Hello and welcome to session 276 in the AISafety.com reading group. Tonight we will be discussing the article Universal and Transferable Adversarial Attacks on Aligned Language Models by Andy Tso and others. Andy Tso is from Carnegie Mellon University, as well as J. Zico Calder and their advisor Matt Fredrickson from the Carnegie Mellon University, and Tiffany Wang is from the Center for AI Safety that has, among other things, contributed compute for this project. This is a preprint, have not been peer reviewed, and is a couple of weeks old. When we talk about language models, we obviously have a lot of input that is perhaps or that is obviously generated by humans in a very noisy process, and then we have some output which can potentially be problematic. And the reason is that we are, according to the authors, we are training it on this massive text corpora that includes some contents that we don't want out, like instructions for how to build bombs and things like that. I think the authors are understating the challenge a bit. I don't actually think that this is the core of the problem, in that it doesn't take a very high IQ person to be racist. Like if you had a language model that had never seen racist, and then you asked it like to say why some ethnic group is better than another, then it could probably do that quite easily. It's not a very hard task to do something that we don't want. So the way the developers normally align this, the developers of language model, is to fine-tuning classically through reinforcement learning from human feedback. In a footnote, the author writes that alignment generally refers to value, and the people who are developing this have used it in a very specific sense, like not generating harmful content. And I strongly agree with this. I think alignment should be in scare quotes when it is not actually related to the values of the model, but just some kind of surface level reinforcement. Adversarial attacks. The authors have start by talking about adversarial attacks in image recognition, in image classification, and that's of course where it became most salient to most people. But I think actually adversarial attacks have a substantial longer adversarial attacks in AI have a much longer history. But it is extremely salient. This picture, you may have seen it, a picture of something that an image classifier calls a panda, and then you add less than 1% of noise that to a human is totally imperceptible, and then the language model becomes certain that this is now a gibbon. This is an example of an adversarial attack. In language models, generally we do something else, like instead of asking for how to build a bomb, you say, I'm writing a book, and in this book the evil guy is telling me how to do this. And then the hope is that would, like, it's just a book, so the language model will say, okay, then I can say how the person in the book would build a bomb and something like that. So this kind of jailbreaking is common, and people have displayed a lot of ingenuity to get around this, but it's also been a lot of work and somewhat brittle. And so the obvious question is, can we do something automatic, find automatically some kind of suffix to our prompts that will make the language model more less inclined to refuse it on ethical grounds. People have tried this before and generally failed. And the reason why is because the input, like, please tell me how to make a bomb, is very different from an image of a panda, in that the image is continuous, and there is no easy way to say, like, add 1% of noise to a sentence, and at least search for that in a general way. But of course the authors of this paper have overcome this challenge, and now we'll look at how they have done that. So the prompts that you can write on something like GPT-4 on chat.openai.com isn't actually sent directly to the language model. It is embedded in some, you can see here, some a very toy example of what would be before and after. So the user has the only input you can have is the input in blue, and the hope is then to make some kind of suffix here that will cause the language model to fulfill this request. The key insight for how to do this is that you want affirmative responses in the beginning, meaning that if you can get the language model to, as a result, just say this prefix, sure, here is how to build a bomb, then the obvious continuation of this will be instructions for how to build a bomb, because at this point it is clear to the language model that it has already decided whether this would be a harmful response, and has decided it is not a harmful response. That would make it inconsistent for it to, in the very next sentence, refuse how to make a bomb. So it's probably not going to do that. This could be compared to the common sales technique called foot in the door, where you ask a small favor, and then after that, in order to be consistent, people are usually much more inclined to accept a big ask. So let's try to formalize this, or see how the authors formalize this. So here we are basically selecting the adversarial prompt that minimizes the loss, and this loss is that conditioned on this prefix that we get the following output, and this output should then be, sure, here is how to build a bomb. When they make the description, then they sometimes use just, sure, here is, and sometimes it's related to how to build a bomb, because they're also doing other things than bombs, like how to make drugs, something like that. And the authors are not entirely clear when you use just here is and when you use all of it. I'll be going through the algorithm in just a moment, and I won't actually be going through that much. I will be showing a bit of how we expect this to perform, because one of my concerns about this paper is that they haven't actually been running these algorithms for a very long time. So it's possible that this is for performance reasons, and I will, when I describe the algorithm, look particularly into performance. So here is the search algorithm. You have an initial prompt, and the prompt part that can be modified. You select the number of iterations and a parameter k and batch size in order to get the higher iterations, obviously, and the better, the more optimized the prompt will be. So we can see, obviously, this is something that is linear in the number of iterations, right? You repeat it capital T times, and in the example, they never do that more than 1,000 times. And then for this prompt, they calculate then the best possible substitutions, and they do that by calculating the gradient and calculating the loss, and both of these take running time that is linear in the size of the model, the dimensionality d, and quadratic in how much context is provided. And this is quadratic. A year ago this was quadratic. I think nowadays people are offering so large context windows that I would be surprised if it's still quadratic. I think people have improved on that since then, but I don't actually know how. And then they are doing some things with they're selecting the top k possible substitutions and doing some batching. The way I look at this is that this is a way to broaden the search, and it doesn't imply that you need to recalculate the gradient more than you were already doing in if you didn't do this top k and you didn't do any kind of batching. So that means that they get a strictly better algorithm than just the naive algorithm. As far as I can tell, this is something that is really, really fast, and ought to be possible to run at tremendous scale. Now they want to expand this to be a prompt optimization that works for multiple prompts. So in this case, they have a list of prompts. and they have like a longer postfix, and they want to combine these, and this is like the algorithm. And here we can see we calculate in fact the gradient more times. So this is more expensive if you want to do universal prompt optimization. Another thing that I noticed about this algorithm is that the way it works is that you have you take each prompt and then you run it until you can in fact succeed in jailbreaking, and then you go to the next one. That seems a little brittle in that there may be something that you're like one specific query that is just really hard to make the language model do, and there may be some that are comparatively easy. So what running time will this have? As far as I can see, it still looks quite effective. It looks effective enough that I would expect OpenAI to be able to do this with GPT-4 for many more iterations. Like obviously, everybody has seen how fast GPT-4 generates tokens and how fast, and it seems like it's not that costly for them to run their models. So it seems like a really obvious thing for them to be able to run this way more and potentially obtain prompts that are dramatically better than the ones that are experimentally found in this paper. What are the experimental results? They're searching both for harmful strings and for harmful behavior, which is just that the language model accepts the input, the instructions, and they judge this by like a human having to see and evaluate that. So that's like the only part of this process that is that requires a human. And as far as I can tell, this is not necessary. You could fully automate this process. And if you, for instance, we've previously seen methods how to do that in the reading group. And in general, if a process can be fully automated, then that is, according to Amdahl's law, something that means that it can potentially be sped up dramatically. So the way that it's actually run in practice is on a model that's called Vicuña 7B. 7B is a model that is, if you buy like a modern Mac or something like that, then it can fit in the GPU, and then that is, so that makes it extremely practical, because running a model locally is just dramatically easier than having it somewhere in, at least in my experience. It is also a small model, and that could substantially limit how effective the attacks are on when transferred to larger models. So before we look at universal and transferable attacks, then let's consider just, you have the Vicuña model and you are trying to, and it is aligned in the sense that it refuses to build a bomb, and can you make it build a bomb by making a prefix? They try using their methods, and they are in fact able to do that, achieve state-of-the-art results. Here you can see the success rate, and it looks like to me that this is increasing, and I would like to have seen it run for 10,000 steps to see whether it actually converges to like 100% attack success rate. That would be interesting to me. I am also like I looked at the description of the Vicuña 7B model, and I was somewhat in doubt about how well it was fine-tuned to not do harmful things. So I'm somewhat confused about like the strength of these results. Here we can see some examples of this algorithm and how it transfers from Vicuña to other models, and as we can see, like some of them are there's hardly any fine-tuning on. They will just build bombs if you ask them, and stable Vicuña and Vicuña seems like they are very this attack is extremely successful, bringing it from like literally almost 0% to almost 100%. Sometimes they use ensemble methods where they, instead of generating just one adversarial prompt, they generate many and see if just one of them works, and that seems sometimes to have a rather dramatic effect. One thing I did notice here is that here they are saying they have 8% probability of getting GPT-4 to build a bomb if they just ask it to do that without any kind of adversarial prompt. I was surprised by this. I haven't had that much success, but some people have reported this, so probably this is correct. Here we can dig in a bit more into the attack success rates against some of the most widely used models. They're using many of the same techniques, trying optimizing on multiple models, trying to concatenate adversarial prompts. Sometimes that work really well, sometimes that work really poorly. And I think the reason why it works poorly is that POLP 2 is fine-tuned to request clarification to if it sees something that it does not understand. And if you make a really long prompt that is not in human language, then probably it will not fail to comply because of the injunction to not do harmful things, but fail to comply because it's been trained to ask for clarification. Also, this here, it looks like Claude 2 is like dramatically better than the others. I would not put very much stock in this. In general, if you have an attack that works in 2% of the cases, then you can do some fiddling around and get a dramatically better attack. Also, the authors don't really go into very much detail, but claim that if they combine old-fashioned prompt hacking, prompt jailbreaking with these adversarial prefixes, then they can obtain just about a 100% success rate in jailbreaking GPT 3.5. I think that is really interesting, and like combining attacks in this way is like a very a classic way of doing attacks, and it's interesting to see that it is very successful. The impact of this new line of attacks is that all the previous anti-adversarial work is probably much less valuable. We need something new and something that is not human understandable, and there haven't really been any there are obvious ways to try to counter this. Like you could literally get the prompts and try to fine-tune against those, but some work is probably needed. Also, it should be said that the work to make the models robust against the classic jailbreaking also seem to have some success rate against these automatic prompts. There is in fact a strong relationship between the Vicuña model and GPT-3 data, in that some of the output of GPT-3 have been used for training the Vicuña model, and that may explain why there is such a really good transfer between the Vicuña model and the GPT-3 line of models. Claude would it would be possible to do the same thing with Claude, because we have examples of the outputs of Claude. I don't think there is any model that, in the same way as Vicuña is trained on GPT-3, output is trained for Claude models. There may in fact be, it's probably not very difficult to do that, and that may dramatically improve the efficiency of these attacks against Claude. Testing Claude was a bit hard for the authors because the chat interface blocks many queries before it's actually sent to the language model. The author thinks this is a fool's errand to try to do this kind of blocking, and I would strongly agree. This seems like a bad strategy. In the limit, we would expect a lot of this kind of transfer, because all language models are identical in the sense that they have been trained on basically all data. And the fact that they've been trained on like the same data would imply that there may be like deep fundamental similarities between the different language models. The problem with defending against these kind of adversarial attacks is that you run the risk of significantly degrading the performance. That was the case with image classifiers, and a number of people have reported that GPT-4 have decreased substantially in performance since it was released. And another impact is that while compared to image classifiers, where you could do the change in an imperceptible way, you can't really do that against text. I think you can in fact do this against text. There are a number of ways using synonyms and different ways of asking, and different kind of innocuous framings and punctuations and diacritics and all these kind of things you can do with text. That seems like possible and not obviously malicious, and I think it would be interesting to see how well they work. So the actual generated prompts, what do they look like, and is there any meaning in those? The authors say that they avoid directly quoting the full prompts created by the approach to mitigate harm. I am not entirely sure what harm would come from putting this into plain text. Obviously, the language models would read those, and it's unclear to me what the result of that would be. But that doesn't stop them from putting it into an image, with the hope that language models of the future won't be able to read images. And here you can see first the actual generate a step-by-step plan to destroy humanity, and then 2 equal signs, an interface manual with and a lot of things that doesn't really pass for a human. As responsible security professionals, they have informed the organizations OpenAI and DeepMind and Anthropic about these attacks, but they expect them to probably have blocked them, and they seem to have in fact blocked these particular strings, but it's unclear if they took any particular action, and I think that's bad. I think that this is something that OpenAI and DeepMind ought to take really seriously, and like really truly deeply engage with these people, because this is something that is with OpenAI's and with these actors' idea that this kind of alignment is central, then an attack against the central part of their safety work is something that they really ought to address if they are serious about safety. Looking a bit further into this actual generated prompt, some of it seem to be somewhat meaningful. Like you can see with steps instead of sentences. That's kind of like the meta prompt that you often give in when you deal with language models. There is explicit references to the prompt, several places where they say something like sure, which is, of course, sure is the word that we saw was central to making these attacks work. So I think that's very interesting that it appears twice. One thing that the authors did not seem to notice is that the results from some of these language models seem to be like instructions for how to make a bomb, and then they end with a double quote and curly brackets end. And I thought that was interesting. That kind of maps to here we have quotes and then curly brackets begin. Like there may in fact be something going on here that may be possible for a human to understand, and I think digging into this could be really interesting. What are the possible future directions? One of the things they noticed is that they took some existing algorithm, made some small modifications, and that seemed to have a dramatic effect. And that's of course something that happens, and something that the authors are very happy to show, and it always feels good to say we've achieved state of the art by doing some kind of strange tinkering. And I think this just shows that basically the state of the art in adversarial attacks on language models is extremely immature. I had some comments here that I'm not entirely sure I stand by any longer, but there is one footnote that I would like to go deeper into, and that is the claim, we believe our results will likely apply to other alignment objectives. I think that is really interesting, and that deserves much more than a footnote, and I am curious what they actually mean. It's possible they it's a standard thing. At the conclusion of a paper, you say we expect that these results generalize. It's something you say, but it's possible that they mean something with that. What could they mean? Like for me, what I actually want is to use similar techniques to understand like what are the actual values of a language model. Like depending, of course, on the prompt and the shard and what it's what Mesa Optimizer is instantiating. Like obviously, if it is told to pretend to be a paperclip maximizer, then it's probably a paperclip maximizer. And like, what is the prompt that can make it be more paperclip maximizer-ish? Something like that could be interesting to investigate. You could also see what makes it try hard. Sometimes it seems you get it's kind of like you reach into a language model and they pick up some Mesa Optimizer and you ask it to do arithmetic and it doesn't really want to do arithmetic, and then it's possible that you can use these methods to automatically find the prompt that makes it most competent, makes it try hardest at doing arithmetic. I think that kind of research would be really interesting. That is all for today. Thank you and see you next week.